Hey everyone, welcome to today's Explainer. We're going to jump right in and unpack the anatomy of a super specific, high-impact role in the automotive industry. Today, we're zeroing in on the FEA Engineer for batteries at Euler Motors. They're an incredibly innovative EV company based out of Delhi. You know, if you've ever wondered who actually makes sure the powerhouse of an electric vehicle doesn't just, well, fail under immense pressure, you are in the exact right place. So let's dive into this. All right, to start things off, picture this. What actually makes an EV battery safe and reliable? Think about it. It's a massive engineering puzzle. You're dealing with incredibly high voltage, intense thermal energy, and literally constant physical vibration from the road. Before a battery pack ever gets attached to a chassis, it basically has to be virtually indestructible. And that right there is exactly where the FEA engineer comes into play. Over at Euler Motors, they don't mess around with expectations. Every battery pack has to hit 5 absolute non-negotiables. It's got to be structurally safe, highly durable, incredibly reliable, able to withstand some really brutal operating conditions, and it has to do all of that while still meeting strict design and performance targets. Seriously, if even one of those targets is missed, the entire vehicle is compromised. So the FEA engineer is essentially the behind-the-scenes hero, making sure every single one of these objectives is nailed down before physical production even starts. So how exactly do they pull this off? 2 words: finite element analysis, or FEA. Let's just strip away the jargon for a second. Think of FEA, and really the broader field of computer-aided engineering, as the ultimate, highly advanced virtual stress test. By using complex structural simulations, the engineer can actually predict exactly how the battery's internal components will react to real-world forces. It lets them optimize the whole design without having to build and then break hundreds of insanely expensive physical prototypes. Section 1. Core engineering responsibilities, from virtual models to reality. So what does the actual day-to-day workflow look like? Well, it builds chronologically through 4 main phases. First up, you're building the CAE models. Second, you run the actual structural simulations. Third, you post-process those results. And finally, you output actionable engineering analysis. It's just this constant, logical loop of building, testing, analyzing, and refining. Let's zoom in on step 1 for a second. The engineer takes raw 3D CAD geometry of the battery's internals and totally transforms it into CAE-ready finite element models. And this is highly active work. You're setting up intricately detailed meshes, you're defining the exact material properties, establishing contacts, and setting up the boundary conditions that are going to perfectly mimic real-world physical constraints. Once your virtual model is built, the simulations kick off. But you aren't just looking at the whole battery pack from a bird's eye view. You're running simulations at the overarching system level. Then you zoom into the subsystem level, and finally, you go all the way down to the tiny individual component level. This top-to-bottom approach guarantees that absolutely nothing slips through the cracks. After the simulation runs, we enter post-processing. Honestly, it's kind of like a high-tech treasure hunt. You're rigorously scanning the results, hunting for areas of high stress, weird strain, or unwanted deformation. You're actively trying to find potential failure locations so you can evaluate the true structural performance of the design when it's put under extreme pressure. But hey, just finding the weak spots, that's only half the battle. The ultimate goal of this entire life cycle is to deliver actionable feedback. You're analyzing all those simulation outputs to put together technical reports, offer concrete design improvements, and suggest structural optimizations. You're not just pointing out the problem, you're actually engineering the solution. And you won't be doing this in a vacuum either. What's really cool about this role is how cross-functional it is. You'll be working hand-in-hand with the battery design team, the product release team, and the broader vehicle engineering team. Together, you all define the crucial operating scenarios, the load cases, and the exact simulation assumptions that are going to guide your entire workflow. Ultimately, it's a perfect balancing act. On one side, you've got your virtual CAE models and assumptions, but those constantly need to be checked against physical lab testing. You'll actually coordinate with the lab teams, helping with instrumentation and data collection, so you can correlate your virtual results with actual physical test data. That's how you prove your virtual assumptions actually hold up in the real world. Next up, essential software and tools, the engineer's toolkit. All right, the source material throws a whopping 9 complex software programs at us. To keep it from sounding like a textbook, let's break them down by category. For your core simulations, you'll need expertise in heavy hitters like ABAQUS, ANSYS, OptiStruct, and LS-DYNA. When it's time for post-processing, you're looking at HyperMesh, HyperView, and ABAQUS viewer. And finally, for handling CAD and fatigue analysis, you'll lean on SOLIDWORKS and nCode. Honestly, mastering the specific toolkit is basically the FE engineer's superpower. Are you the candidate? Let's check out the qualifications and experience. So what does the ideal profile look like? Education-wise, you need a B.Tech or M.Tech in mechanical engineering or mechanical and automation engineering. As for experience, they're looking for that sweet spot, 2 to 4 years total, preferably in the automotive industry, and ideally with direct hands-on experience in EV battery structural CAE. But listen, it's not just about the years on your resume. Rock-solid fundamentals are an absolute must. You have to really understand the strength of materials, solid mechanics, and machine design. And here's a great insider tip. If you happen to have experience in explicit dynamic analysis, that's going to give you a massive advantage and really make you stand out from the pack. And hey, if your current job title isn't exactly Battery CAE, don't sweat it. There are several adjacent engineering roles that are a fantastic fit. If you're coming from crash and safety CAE, automotive simulation, durability and fatigue analysis, or mechanical design validation, your skills are highly transferable and super valuable for this specific position. All right, if you've been nodding along this whole time thinking, yep, that's me, here is your direct call to action. Euler Motors wants to hear from you. You can send your resume straight to minu.sing@eulermotors.com. Seriously, don't wait around if this sounds like you. Jump on it. Even if you aren't applying right this second, you should absolutely connect with Euler Motors online. They are super active on Facebook, Instagram, LinkedIn, and even WhatsApp. It's just a really great way to catch regular updates, drop them a suggestion, or maybe explore a collaboration down the line as they keep growing. Well, we've covered a lot of ground today, and I want to leave you with this one final thought to wrap up our explainer. Are you ready to actually engineer the future of safe and reliable electric vehicles? This whole transition to electric mobility completely relies on engineers who can master virtual simulations to build unbreakable physical realities on the road. It is a massive challenge, for sure, but an incredibly rewarding one. Thanks for hanging out with me for this deep dive, and as always, keep learning.